Alright, this is my second magnetism explainer video. This time I'm going to talk about forces and interactions, I guess, between magnetic fields and extended objects, instead of just individual charged particles. Extended objects are made up of many charged particles, so there's going to be something going on there. This first slide is about something that happens when you move a conductor through a magnetic field. And the name of it, as you can see, is the Hall effect. As always, you don't need to know the names or be able to identify them or refer to them by name for the AP exam, but it can be helpful to have labels for ideas to help you code the idea into your memory, or to refer to it when you're talking to people about the content. So this phenomenon is called the Hall effect. The idea is that I have this rectangular block of metal, although it doesn't have to be a rectangle, moving through a magnetic field. For simplicity, I'm saying the magnetic field is uniform, but it wouldn't have to be uniform for this to happen. And I'm just saying that the block is moving to the right with this speed v for some reason. We're just going to say it has a constant speed. We'll see some related material, some related ideas when we're studying electromagnetic induction in a couple of weeks. But for now, let's just say it has a speed v for reasons. So because the block is made of matter, it has positive and negative charged particles in it. Because the block is a conductor, those charged particles are able to move around within the confines of the block. And so if you go through a right-hand rule here, you'll find that the positively charged particles are going to feel a downward force, and the negatively charged particles are going to feel an upward force. So that moves pluses down to the bottom of the block, moves negatives up to the top of the block. And that gets us to the situation in my second diagram where I've drawn it as being polarized. The electrons are bunching up at the top. That means that there is a lack of electrons down at the bottom. And the longer the block is moving through this field, the more electrons are going to get bunched up at the top, and the charge separation, or the polarization, will get stronger and stronger. But there is going to be a limit to how strong the polarization gets, because as I polarize the block, I set up an electric field inside the block. That electric field goes from the plus to the minus, and the orientation of the B and E fields here may remind you of the velocity selector or the crossed fields situation that I talked about in the previous video. So the idea is that as this electric field gets stronger and stronger, there will come a point where, if I imagine some new charged particle, if I'm thinking about this electron here in the middle of the block, there's going to come a point where the electric field is strong enough that the net force on this electron is 0. There's still going to be an upward magnetic force, but the electric field exerts a downward force on it. And so once I reach that point, once the polarization is strong enough to satisfy this V equals EB condition that we saw with the crossed field setup, at that point the polarization will stop getting stronger, and it'll sort of stabilize into a steady state. So the electric field strength that we're looking for is V times B, velocity times the magnetic field. And if I name the size of the block, this vertical distance, I'm just going to call it d. And for simplicity, let's pretend that the electric field in the block is going to be uniform. So I know that the potential difference between the top and bottom of the block should be the electric field times the distance. And I know from above that the electric field should be velocity times magnetic field. So this potential difference, VBD, like that is the voltage that I am building up to. If the block is motionless, the charges will just spread out nicely, and there's no potential difference. But if I am dragging it through the field, I generate this voltage, this potential difference, or this EMF, between the top and bottom edges of the block. So this quantity, as it says, is also called a motional EMF. In this particular example, since there's nowhere for current to flow, talking about the EMF is a little bit weird. But again, an almost identical phenomenon will come up in a couple of chapters where there is a way for current to flow. And talking about the EMF there makes a little bit more sense. But the motional EMF, which you'll see again in a couple of chapters, is kind of like an application of the Hall effect. Now, I do have this little parenthetical statement here that I should make mention of, which is that you might be remembering when we studied electrostatics, one of our rules was the inside of a conductor can't have an electric field. And that was actually like an important piece of reasoning in a lot of examples for figuring out how much charge will there be on a certain surface, or we used it when doing some reasoning with Gauss's law as well. Electric fields cannot exist inside a conductor. There was a caveat with that rule that I tried to say every time. Probably didn't succeed. But the caveat was that the conductor has to be in equilibrium for you to be positive that there can't be an electric field. If the conductor is not in equilibrium, then there can be an electric field. One obvious example of that is a wire that's carrying current in a circuit, because the reason the current flows is that there's a force being exerted on the electrons to make them move, and that force comes from an electric field. So when a wire is carrying current, there is an electric field inside the wire, and that's why the current moves. Similarly, this block is not in equilibrium either, because there's a bunch of, without getting into specifics, there's a bunch of like stuff going on. If you stopped forcing it to move through the field, then it would be in equilibrium, and the charges would redistribute themselves in order to get rid of the electric field. But in this state, it is not in equilibrium, and so the field is there. So anyway, if you move a conductor through a magnetic field, it's going to become polarized or generate an EMF or potential difference, something along those lines. And if you need to attach any math to it, it is the same math as from the cross fields velocity selector stuff. So that idea comes up occasionally on the exam, not necessarily every year, but it's relatively common. But something that you will definitely see on the exam is the force exerted on a current-carrying wire. An electrical current is just a whole bunch of charged particles moving. So since we know that magnetic fields exert a force QV cross B on moving charged particles, then the field should also exert a force on any current that flows through the field. The equation that describes that current is here. Instead of QV cross B, it's IL cross B. There's a careful way of going from QV cross B to IL cross B. And if you want to see the careful way of doing it, like it would be in the book, there are lots of places you can look it up. But in my view, the two equations are basically the same equation. And so I have a very quick and dirty version of it right here, which is that v in the qv cross b is like a distance per time, or length per time. So if you just take the time and you move it from underneath the distance to underneath the charge, then you have current times distance, or current times length. That's effectively all there is to it. So they are basically the same equation. Now, I do need to point out, as it says under the red box, that that formula is for a straight wire in a uniform magnetic field. If you don't have a straight wire, then, as I've written down at the bottom, you can make an integral version to handle that. So if the wire is like all bendy or curvy, you just imagine splitting the wire up into infinitely many parts. Each individual part then is straight, and you just calculate the force on each part and you add all the forces together. If the field is non-uniform, you can use the same solution. You break the wire up into infinitely many parts. Then for an infinitesimal part of wire, the field there is uniform because you're looking at such a small piece. And so you just calculate all the forces and add them together. The other thing with this equation that you will occasionally see is this phrase, force per unit length. They literally mean force per length. So if you see that phrase, don't get thrown off by it. Every year I have students who run into questions with that phrase, and they're like, what the heck is this? It's literally in the words, force over length. So you would take the IL cross B and divide it by L. Now, the way I've written it here, notice that the L now has a hat instead of an arrow on it. I've turned it into a unit vector with length 1. The only reason I've written it that way is that since current is not itself a vector, I can't like put the vector hat on the I. That's not physically appropriate. But the idea is you just divide everything by length. Now you might wonder, like, why would we bother to deal with this? And the reason is that if, for example, the wire in your question is infinitely long, which is a thing that physics problems will do, they'll say you have a very long straight wire. Very long means infinite in physics problem speak. So if the magnetic field is also infinite in extent, like if it fills the whole universe, then the total force on the wire is going to be infinite because you have an infinitely long wire in an infinite, in a field of infinite extent, etc. And so you wouldn't be able to calculate F. But each individual meter of the wire has a finite amount of force on it, and so you can calculate that. It can also come up in a question where they just don't want to state. They don't feel like telling you how long the wire is. Maybe it doesn't matter how long the wire is, but you could still find like the force per meter of wire. That can be a useful number. So I'm going to show you one additional thing today, which is that if you have a complete loop of wire that's carrying current, there's two important things to know about that. First thing, as I have on the top half of my screen here, is that the net force on that wire is going to be 0. It has to be 0, because by nature of having a complete loop, there's as much current going in any particular direction as in any other direction. It's easiest to think about with a rectangle, I think, but a perfect circle you might also be happy with. But with this rectangle, I have 4 distinct segments, each with a force on them. But it should be pretty clear, conceptually speaking, that those forces are going to cancel each other out, as long as the field is uniform, at least. Like, I have to have the same amount of current at all points on the loop. And so if the field also has equal strength everywhere, then there's no net force. In the example that I've drawn, there is sort of like a tendency to stretch out the wire. So like if the wire is made of something soft, like if it's a very either malleable or ductile, one of those. If it's a very ductile metal, then it could be that it's going to get stretched out, but not necessarily. Depends on how strong the forces are. If I were to reverse the direction of the current or the field, then the forces would all point inward instead of outward. So that can be either, they don't have to go outward, they could go inward. It depends on the directions of stuff in the right-hand rule. But regardless of whether they point in or out, the total force is still going to be 0. So that's important. However, even though the total force is 0, there can be a net torque, which can cause the loop to rotate or to have an angular acceleration. And so in my lower diagram, it's supposed to be the exact same situation, but instead of like looking face on at the loop, you're looking edge on. So instead of the magnetic field coming out of the screen, the magnetic field's going up. And again, we're looking like almost edge on the loop. I drew it a little bit in perspective. So this front edge of the loop has a force that comes out of the screen. The back edge has a force that goes into the screen. And again, those are just going to cancel each other out. But if you look at the left segment, it has a force that goes to the left, but that force has to be perpendicular to the magnetic field, which is not perpendicular to the plane of the loop. Similarly, the right segment has a force that goes to the right, but there's like an angle there between the loop itself and the direction of the force. And so those two forces would tend to, if the loop is on an angle like that, the two forces would tend to sort of get it to flop down to this position. Like this horizontal position, a position that's perpendicular to the field. That's the position that like it wants to be in. And that does depend on the direction of the field and or the current. So on the left, I've drawn the stable orientation. So with this magnetic field going up, then if the current goes around it that way, the way I've drawn it, and this part here, that's in front of the field line. So if the current is oriented that way, which is close to what I've drawn above, that's a stable configuration, where if you like bump it out of alignment slightly, it'll just sort of like flop back and forth like this. But if the current is going the other way around the magnetic field, you could get it perfectly balanced horizontally, but if you nudge it at all, it's going to flip over the whole way to get into the stable configuration. Now the way that I can tell which way is which is by either drawing a complicated diagram like this with the force vectors, or by using a right-hand rule. So the idea here, all of the right-hand rules are basically the same rule, but if you think of your thumb as being the magnetic field, your fingers curl around a particular way, and that's the direction that you would want the current to go in order to have the stable or like favorable, energetically favorable orientation. So anyway, when the wire loop is not normal to the field, you're going to have a torque. And if you need to calculate anything with that torque, you'll have to remember how torque works. That was way back in our mechanics coverage, but the torque vector tau is r cross F. So like the force itself, I just talked about. You can find that by doing IL cross B. And then you would need like an R vector. That's going to depend on where the pivot point is. Typically, with a wire loop like this, there would be like an axis or an axle that goes through the center. So your R vector would like be this. And then you can do your R cross F and figure out how much torque is applied to the loop due to the magnetic field. This principle that you can get a torque on a loop of wire is the way motors work, electric motors. And it is the reverse of how electric generators work. And obviously, electrical generators and motors are rather common in our technology that allows our society to exist. So this is an idea of very large importance to technology. It'll definitely come up at some point in the exam as well, because of how applicable it is to later stuff in physics and or engineering. But it all goes back to just F equals IL cross B, and like our definitions of torque from ages ago. And that is all of the content that you need for the problems that I gave you to work on over break. So if you want more coverage of this, you can read about it, or you can find somebody else's videos. But that's all I had to say, so good luck.